And in this unit, interaction of radiation with matter, we were dealing with the interaction of heavy charged particles with the matter. In that, we have discussed these two properties, nature of the interaction and stopping power. And in the stopping power, we have introduced an equation known as Bethe formula, and we will be applying that Bethe formula in some of these topics. And in this class, we will try to introduce these topics, that is energy loss characteristics, range, energy straggling and range straggling, and stopping time. The remaining terms will be discussed in further classes. So the first term, energy loss characteristics. A plot of the specific energy loss along the track of a charged particle is known as a Bragg curve. And the curve is like this. This is the distance of penetration, and this is the specific energy loss that you are writing as minus dE by dx. So here you can see that this is the shape of the curve. And from this curve, what can you understand? Here, the specific energy loss is minimum and it is increasing as the distance of penetration increases. At a particular point, it is maximum, and that maximum point you are calling as Bragg peak. And after that Bragg peak, there is a sharp decrease, that means no energy loss. For most of the track, the charge on the alpha particle is 2 electronic charges. We are considering an example of alpha particle, and the specific energy loss increases roughly as 1 by E. That means it is inverse of E. Near the end of the track, the charge is reduced through electron pickup and the curve falls off. So when it is reaching a particular distance, its velocity decreases, and at that point or at that position, the alpha particle is absorbing 2 electrons and it is becoming a neutral one. So there, its complete energy is lost. That means the curve suddenly falls off. And you are calling that peak value as the Bragg peak. And this property of Bragg peak is used to treat cancer patients in radiotherapy, where the particle delivers maximum radiation at a given depth without exit dose. That means after that, the particle is stopping there and it is not coming out of the absorber. And protons are well established external beam particle recommended for such precision therapy. The Bragg peak can be modulated and flattened by using a filter to suit clinical conditions. So, for example, if you have that cancer cells are say at a depth of say 2 centimeter, you will be adjusting the position. You have to adjust the position of Bragg peak at a distance of 2 centimeter. So up to that, the specific energy loss will be much small. That means it will not destroy the normal cells. But at a distance of 2 centimeter, if you have some cancer cells there, it will liberate, that proton will give up maximum of its energy. So due to that energy, the cells will be destroyed. That property you are using. And if you are using single particles as well as beams, there will be some difference. You can see that this is the Bragg curve for a single particle. For alpha particle, we have already shown this. And this is this dotted curve shows that of a particle beam. And the difference for a single alpha particle track and for average behavior of a parallel beam of alpha particle of the same initial energy. The two curves differ somewhat due to the effect of straggling. This term, straggling, we will be discussing later. So you just note that term, straggling. So this difference is due to the term straggling. And now we have the definition of range. Range means up to what distance a particle can move. That you are considering as the range. For studying that, you will be considering an alpha source or a source which is placed at a particular point, and you are getting a collimated beam like this, and this is an absorber. Say T is its thickness, and this thickness can be varied. A collimated source of mono-energetic alpha particles passing through an absorber of variable thickness are counted using a detector. This is the detector which can count the number of particles coming out of this absorber, and the result can be plotted in a graph. So this point I by I0 you can consider as its value is 1, and this is half of that I by I0. You can see that up to a particular distance there is not much absorption in the material. It is almost all particles are coming out of the detector and out of the absorber, and after, when the thickness is greater than a particular value, say Rm, you can see that ratio decreases, which means that some particles are stopped within the absorber. That means that distance corresponds to the range of the particle. You can see that after this it gradually falls off and then to a 0. So based on this, you are defining two terms as Rm and Re, a particular type of range, mean range and extrapolated range. No attenuation in the number of alpha particles takes place until the absorber thickness approaches the length of the shortest track in the absorbing material. That is a minimum distance. Up to that minimum distance, there is no attenuation. Increasing the thickness then stops more and more of the alpha particles, and the intensity of the detected beam drops rapidly to 0. The range of the alpha particles in the absorber material can be determined from this curve in several ways. The mean range, Rm, this one, is defined as the absorber thickness that reduces the alpha particle count to exactly 1/2 of its value in the absence of the absorber. That means without the absorber, I0 you have to get. So this I by I0 is reducing to half here. And this distance, that means this thickness, you are calling as the mean range. The extrapolated range is obtained by extrapolating the linear portion of the end of the transmission curve to 0. This curve you are calling as the transmission curve. That means how much particles are transmitted through the absorber to the detector. That is why it is known as a transmission curve. So this transmission curve, you can see that around this portion, here you have a curve, and here it is almost a linear portion, and after this again you are getting a curve. So when you are extrapolating this linear portion, you will be reaching here, and this point you are calling as the extrapolated range, and this extrapolated range will be somewhat greater than the mean range. And you can see that this mean range means this is actually up to this point, all alpha particles are, or all particles are coming out. And after that, the number decreases. So this corresponds to range of some particles, and this is the range of some maximum particles. So actually this is the mean position of that range. That is why you are considering it as the mean range. The range of charged particles of a given energy is thus a fairly unique quantity in a specific absorbing material. That is, same for all identical particles with the same initial energy in the same type of material. This is an important concept. Suppose you are using, say, alpha particle with the 5 mega electron volt energy, and the absorber is a carbon. The range of that carbon in the range of alpha particle in carbon will be a particular value, say 5 centimeter. That's a specified value. If you are using a thick carbon sheet or a thin one, whatever be the nature of that carbon, if that carbon has the same density, that range will be same. So you have the energy and the range, energy of a particular particle and range in a particular absorber will be a constant value, and this can be used as some experimental data. In the earlier days of radiation measurement, the energy of alpha particles was indirectly measured by determining the absorber thickness equivalent to their mean range. And here what we have mentioned is, nowadays actually we are using detectors to find out the energy. But in olden days, before the development of these detectors, an easier method for these detectors, what we did was, you will take some absorber and you are given beam, and the range for your beam through a given type of absorber for a variable thickness of that absorber is known. So if you are varying that absorber thickness, you can see that after a particular distance you are getting no particles out of that. So you can calculate that particular thickness, and from that particular thickness you can have an idea about the range of the particle, and from that range you can get the idea of the energy. And now we have mentioned the term straggling, and two types of straggling as there. Straggling means that it is a variation in a particular. Energy straggling means variation in energy, and range straggling means some variation in range. So as a charged particle penetrates matter, statistical fluctuations occur. Actually, this statistical fluctuation means the energy of a particle is lost due to collisions, etc., etc. But when a particle is moving through a medium, that energy loss depends on the number of collisions. And in a material, it is not actually isotropic. So in a particular direction, the number of collisions will be more. That means number of particles in that track will be more. But in some direction, that value may be slightly less. So there, the number of collisions will be less. That means when number of collisions are less, the energy loss will be somewhat lower. That is the case you are mentioning by this term, statistical fluctuations. So as a charged particle penetrates matter, statistical fluctuations occur in the number of collisions along its path and in the amount of energy lost in each collision. As a result, a number of identical particles starting out under identical condition will show a distribution of energies as they pass a given depth, a distribution of path lengths traversed before they stop. That means distribution of energies means your specific energy loss. There will be variation in minus dE by dx, and distribution of path lengths means there will be a variation in range. So this distribution of energy known as energy straggling and distribution of path lengths as range straggling. So this is your energy straggling. The phenomenon of unequal energy losses under identical conditions is called energy straggling. Here you just consider these only, this first one. Here you can see that at a particular point, this is the value of, it's a function of E and dx that you are considering as actually minus dE by dx. That means variation of E with respect to x distance. That is, you are mentioning like this. So this is the variation. This is the value of dE by dx. And that energy is lost in this small, in a small value, in a small range. Actually, it is only varying in a small range. So this is like this. And when your particle is penetrating the depth, this is that depth x. For a more clear view, you have drawn the graph like this. So here, when it is reaching at this point, say a particular distance. So now this is this point, and here you have to draw this one. So here you can see that that means at a distance, you can see that this is the nature of graph. That means value of minus dE by dx decreases, and that dE by that energy is somewhat wider, means it is not completely dissolved at a small distance, but somewhat larger. So as the particle penetrates, you can see that width increases. That means over a range, energy is dissipating, and the value is also less. It is decreasing. Here you can see that. And here, after that, this is the range is the will be that energy dissipating area or a dissipating length is maximum. But after that, you can see that value is decreasing. And also, the minus dE by dx is also increasing. So here you can have a type of variations. It is decreasing, then it is increasing. So you can see that if you consider different points, on all these different points, here, 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 and here, you can see that the energy losses are different. And this is the same material. That means under identical conditions. So this phenomenon of unequal energy losses under identical conditions is called energy straggling. And now, this we have marked as a energy straggling. Means energy is losing like this. You can see the energy loss is different. And the existence of different path lengths is referred as range straggling. We have already mentioned that here you have more number of particles and here less number of particles. So most number of particles have range up to here, and only suppose somewhat like this. here, here, etc. So, and this is the maximum number. So, this maximum number, this minimum number of particles, and this is the maximum number of particles, and this is you are calling as the range straggling. So, particles have a range from this point to this point, and this is of course your mean range, and this thing you are calling as the range straggling. And the next term is stopping time. That means the time required to stop a particle while it is moving through a medium. And you have actually the expression for, if you know the initial energy, you can have an expression for its velocity by knowing its mass. And we have the classical expression for velocity as distance by time. Here, if you consider that distance as the range, that means when it is stopping, you have the velocity, range and time. That means you can find the time to stop. That means if you know range and velocity, you can find the time. That means the stopping time. The time required to stop a charged particle in an absorber can be deduced from its range and average velocity. You are considering average velocity because while particle is moving through the absorber medium, its velocity is continuously decreasing. So, initially it has maximum velocity, then finally 0. So, always you have to consider an average velocity. And for non-relativistic particles of mass velocity, mass m, velocity v, and kinetic energy E, you can write as E is equal to half mv square, expression for kinetic energy, where you can write as v will be equal to root of 2e by m. You can multiply both the numerator and the denominator with the c square. So here you have c square, here also c square, and this c square coming out of the root sign. So it is c into root of 2e by mc square. You can now substitute the value of c as 3 into 10 raised to 8. And this mc square means it is the energy equivalent to mass. And it will be normally in joule when you consider this m in kilogram. And if you consider that m in atomic mass unit or simply your U, this energy will be in MeV. You can convert it to mega electron volt. So, for that now you are converting this mass into atomic mass unit. So, that is why this is 2e by 931 MeV per AMU. If this A is in AMU, for 1 AMU, we know that the energy is 931 MeV. So, if this is a 1.6 or 1.7 MA, it will be equal to 1.67 into 931. That you can directly get. So, this is the expression where Ma is the particle mass in atomic mass units and E is the particle energy in MeV. If we assume the average particle velocity as its loss is average V is equal to capital K into V, where this capital K is a constant and where V is evaluated at the initial energy, then the stopping time T can be calculated from the range as time equals distance by velocity. That means R is the distance, range is the distance, and average velocity is the velocity. Now you are replacing this average velocity with the kV. So by substituting for this V as C into root of 2E by mc square, it will be R by Kc root of mc square by 2E. Now you can substitute this in terms of MeV as we have done earlier. So this is our expression, R by K into 3 into 10 raised to 8. This is in meter per second. 931 MeV per AMU by 2. And you are of course taking this root of Ma by E outside this. If the particle were uniformly decelerated, then average velocity v would be given by v by 2 and k is equal to 0.5. That is, if it is uniformly decelerated, you can consider initial velocity as v, final velocity as 0, average velocity is equal to v plus 0 by 2, that will be v by 2. So here, average velocity v equals k, this value you are getting as v by 2. So v by 2 is equal to k into v. So value of your k should be equal to half. That is this k as 0.5. However, charged particles generally lose energy at a greater rate near the end of their range that we have seen before, and k should be somewhat higher fraction. By assuming k is equal to 0.60, the stopping time can be estimated. So, you have seen that Bragg curve, their energy loss is maximum at the ends. That means initially the velocity is not decreasing so rapidly. If it is decreasing rapidly initially, this value will be less than 0.5. And now you are simplifying these terms, r 300 raised to 8 meter per second and this value, etc. So you will be getting nearly like this, t nearly equal to 1.2 into 10 raised to minus 7 capital R range in the root of ma by e. Actually, here you have a divide by sign, where t is in seconds, r in meters, ma in AMU and e in MeV. This approximation is expected to be reasonably accurate for light heavy charged particles such as protons, alpha particles, etc. It cannot be used for relativistic particles such as fast electrons. And that's all in this class. We can discuss the remaining terms in next class. Thank you.